this. Come and run again. You want a dose of this right now? It's KDA.
The goal for this set of videos is to cover this review section about strategies for testing series, section 11.7 in Stewart's book. Stewart has this advice around the idea of you're presented with a series. How do you know whether or not it converges? So I'm going to start by just going over all of the different series tests that we learned in order. And then what I'll do is go over Donaldson's advice, which is kind of close to Stewart's, for what to do when you see a series and you're asked whether or not it converges. Okay, so the first series test we saw was the divergence test, or nth term test. And it's often really easy to check this first. That's the one that says you're adding up a series, sum n equals 1 to infinity of an. If the limit as n goes to infinity of an is not 0, your series diverges. So the thing to note, this can only tell you that a series diverges. There's no way for this test to tell you that a series converges. It either tells you that a series diverges, or it tells you nothing. Okay, the second thing we saw was the integral test. And the idea was to compare a series with an integral, where we're taking the integral of a function f of x, where f of n equals the nth term in your series. So there are a couple of assumptions. F has to be non-increasing, continuous, and positive on the interval from 1 to infinity. But the idea is that this series and this integral are linked together. One converges if and only if the other converges. The problem here is that integrating is hard. So usually doing this integral takes a lot of work. So it's often easier to do something else. So this test actually gets pretty rarely applied. Okay, we have the comparison test. That was the one where we have two sequences, an and bn, and for all n sufficiently large, 0 is less than an is less than bn. So we have these smaller numbers, an, and these bigger numbers, bn. And the idea is that if the sum of the smaller numbers diverges, then certainly the sum of the bigger numbers diverges. Or if the sum of the bigger numbers converges, then certainly the sum of the smaller numbers converges also. And this works great when you have a series that's close to a series that you know. So if you have like a sine or a cosine in your an, then often you can get easy upper and lower bounds for your sequence that you could use as your bn's by just replacing sine or cosine with like 1 or -1. It's often hard to find the right series to compare with. Like you're just given a series, sum of an, and maybe there's a good choice of bn where you can apply the comparison test. But it's not usually so obvious what bn you should take. So after talking about the comparison test, we talked about the limit comparison test. The limit comparison test worked great for things that had an with fractions, an with square roots, or like more general roots. This is a very, very common test. This is often the first one that I think to try. One thing I'll say is the limit comparison test and the comparison test kind of go together in the sense that most of the time when the comparison test works, you could also get the limit comparison test to work. And applying the limit comparison test will be a little easier. That's not always true, but a lot of the time it's true. Okay, then we talked about the alternating series test, which if you see a -1 to the n, that's a great sign that you have an alternating series, a series whose terms flip back and forth, plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus. And the plus for the alternating series test is that it's very easy to apply. So if you have a sum of -1 to the n times bn, and that bn sequence is positive, all you need to know is that the bn sequence is decreasing, and the limit as n goes to infinity is 0, and you know your sequence converges. The last two tests we talked about together, the ratio test and the root test. The ratio test is very common also. It's great for an, where you have like a ratio of things, or if you have things like n factorial or an exponential function like 2 to the n. And the reason that the ratio test is good there is that when you take an divided by an plus 1 divided by an, you get a lot of cancellation. So you end up taking the limit of this quantity. If there's a lot of cancellation, that limit is often pretty easy to take. And finally, we had the root test, which was like the ratio test, but we looked at something a little different. Instead of the limit of absolute value of an plus 1 over an, we looked at the limit of absolute value of an to the 1 over n power. That 1 over n power cancels really nicely if your an is something to the nth power. So if you have something to the nth power and you raise it to the 1 over n, you'll just get something to the 1. So the root test works really nicely in that particular case. Okay, so those are all the tests that we saw. So I'm going to pause and erase and then talk about Donaldson's advice for how to decide like which tests to apply in which order. So let's talk about what to do if you're presented with a series S, a sum from n equals 1 to an, and you want to know, does S converge? So we have all these series tests. Which one might you want to try first? Well, often it's a good idea to just take a second and try to apply the divergence test. That means we look at the limit as n goes to infinity of an. And sometimes this will tell you that your series diverges. But most of the time, the limit of an is going to be 0 for the problems that you see, like on a quiz or in an exam. So you have to do something else. So if the divergence test tells you the series diverges, you're done. If not, you could ask, is this some kind of standard series that I should recognize? Meaning something like a geometric series. Maybe your series doesn't look like a geometric series right away, but after some algebraic manipulation, it becomes a geometric series. So if we have a real number r, remember this geometric series, this converges if and only if the absolute value of r is less than 1. Let me write this on a new line. If the absolute value of r is less than 1, and in that case, we even know what it converges to. It converges to 1 over 1 minus r. This is the formula for a geometric series that we know holds anytime the series converges. So what other standard series do we know? Something like a p-series, which is a sum, n equals 1 to infinity of 1 over n to the p. And we know this converges if p is bigger than 1, and diverges if p is less than or equal to 1. And this was one that we saw using the integral test. So that's why we introduced the integral test when we did, so that we could understand p-series is one of our standard series to use for comparison and everything else. Okay, so we've already tried the divergence test. We've seen if our series is like a standard series, like a geometric series or a p-series, great. But if it's not, we have to do something else. So maybe you want to divide up that something else into tests for absolute convergence versus tests that just tell you whether or not S converges. Right? Because sometimes you'll be asked not only whether S converges, but whether S converges absolutely, which means S converges, but also S plus converges. The series that you get by putting in absolute values around the ANs. Okay, so what are the series tests that we know that tell you about absolute convergence? We know the ratio test is one, right? That the ratio test is all about the limit as n goes to infinity of the absolute value of an plus 1 over an. And then we also know the root test, where we ask about L is the limit as n goes to infinity of absolute value an to the 1 over n. In both cases, if L is less than 1, then S not only converges, but converges absolutely. If L is bigger than 1, then S diverges. And if L equals 1, you really have to do another test. So we've already sort of said cases where the ratio test or the root test work well. So there are ways to make some of the other tests into tests for absolute convergence, where you have something like the limit comparison test or the comparison test. And instead, when you use the comparison test, instead of having like 0 less than an less than bn, you would want to look at 0 less than absolute value of an less than absolute value of bn. This is in Donaldson's advice in the notes, but I sort of prefer to keep the limit comparison test and the comparison test a little bit separate from the ratio test and the root test that definitely are telling you about absolute convergence. So I wouldn't think of this, these tests as being like absolute convergence tests. So we have all our other tests. And yeah, I guess I'll write this here. The limit comparison test is often easy to apply. So if I have a problem that doesn't necessarily ask about absolute convergence, then I'm not necessarily going to jump straight to the ratio test or the root test. Instead, I might try the ratio test if my an is given as like a ratio of something or has an n factorial or an exponential like 2 to the n. But otherwise, I might try the limit comparison test. And in particular, this idea of let bn be the ratio of highest terms. Bn be the ratio of highest terms if your an is given to you as a quotient of things, and you take the highest power of n in the numerator and the highest power of n in the denominator, often the limit comparison test works really well. And then I sort of think of, we have these other tests. We have the comparison test. I said something about like when you have a sine or a cosine, and in some other situations, this works. But often, anytime you can use a comparison test, it's better to try using the limit comparison test. Then we have this one that's kind of a last resort, that is the integral test. And I try to avoid using this at all costs. What I would do is look back at the examples that we did in the videos for the integral test. There are a couple of examples that work well for the integral test where it's not so clear what to do with other tests. But this one is rare. And then we have our last test, which is a little bit separate than the others, this alternating series test. It's kind of in its own category because it only applies when your series is alternating. All these other tests we can apply no matter what. Like, it doesn't require that our series terms flip back and forth, positive, negative, positive, negative. The alternating series test does. So if I see an alternating series test, maybe I would try the divergence test first to see whether or not the things I'm adding up are going to 0. But if that doesn't tell me that the series diverges, I would jump immediately to the alternating series test. It's easy to apply, but it only applies in special situations. So I'm going to pause and erase, and I'm going to talk about one extra little issue, which is sometimes you're not just asked for whether S converges, but you're also asked to give the value of S. Like, you're told that it's going to converge, and what is the value it converges to? So that really only comes up in a few special examples, so I want to talk about those first. All right, so in the last part of this video, I just want to talk about values of series. So maybe you're asked, here's a series, S is the sum from n equals 1 to infinity of an, and you're told if S converges, give the value it converges to. So it's not enough to say that S converges, we want to say what it converges to. So that's a great hint that your series is going to be of one of two special types. The first is a geometric series, where we know that when the absolute value of r is less than 1, the sum of n equals 0 from n equals 0 to infinity of r to the n equals 1 over 1 minus r. So in the case that a geometric series converges, we know the value that it converges to. The other special case is a telescoping series. And what is a telescoping series? We're adding up infinitely many things, but there's some special cancellation going on so that there's only finitely many things that don't cancel out. So here's an example. Like we have a sum from n equals 1 to infinity of 1 over square root of n minus 1 over square root of n plus 1. And if you start to write out the first few terms, you see a pattern. So we get 1 over square root of 1 minus 1 over square root of 2, plus 1 over square root of 2 minus 1 over square root of 3, plus 1 over square root of 3 minus 1 over square root of 4, plus 1 over square root of 4. And what we're seeing is the negative term in each pair cancels with the positive term in the next pair. Minus 1 over root 2 plus 1 over root 2, minus 1 over root 3 plus 1 over root 3, minus 1 over root 4 plus 1 over root 4. So this series is equal to 1 because the only thing that never cancels is this 1 over square root of 1. So you should expect to see some questions on the final exam where you're asked for the value of a series, but you should immediately think, that's going to be a question either about a geometric series or about a telescoping series. So for the rest of the videos for this lecture, we're just going to do a bunch of examples. I'll give you some series, and we'll talk about how to decide what tests to try to see if this series converges.